Okay, so up to last class, we have started acceleration due to gravity, and we were doing variation of acceleration due to gravity with height. We were doing variation of acceleration due to gravity with height. So the last equation where I left was this g prime is g by 1 plus its h by r whole square, right? In the next step, you can simplify this expression. To simplify this expression, you can do one thing. Take this 1 plus h by r in numerator. So this is, it's 1 plus h by r to the power minus. Now, to open this power minus 2, we can use an approximation. An approximation is, I'm using one approximation to simplify this expression. Otherwise, the final result is this, g prime is g 1 plus h by r whole square. But just for the sake of simplification, we can use an approximation. And that approximation says that height is very, very less than the radius of Earth. So the height at which we are taking the body is very less than the radius of Earth. Radius of Earth is, it's roughly 6,400 kilometers. So the height is much less than 6,400 kilometers. So height is very, very less than r. So your h by r is very, very less than 1. If h by r is very, very less than 1, then we can use binomial expression. We can use binomial expansion. See, what is binomial expansion in mathematics? Binomial expansion simply means if you have term like 1 plus x to the power n, this n could be any power. If this n is 2, then you know this expansion like 1 plus x square is 1 plus x square plus 2x. If I put this n equal to 3, then you too know this expansion. But instead of 3, if I put any other value, like I write this as minus 4 by 3. Then to expand this expression, you will need binomial expansion. So the binomial expansion says if 1 plus x to the power n, if x is less than 1, then you can simply write this as 1 plus x. It's an expansion. The expansion like square, cube, if you have 1 plus x to the power n, under the condition that x is very, very less than 1, then this is 1 plus nx. There are few more terms, but those terms are very small. You can ignore those. So the leading terms is just 1 plus nx. This is binomial expansion, a topic of mathematics that I will use here. Let's call this as equation number 4. So if I expand this term 1 plus h by r to the power minus 2. Instead of n, we are using minus 2. And instead of x, we are using 1 plus h by r. So we expand it, this is 1 plus n. Instead of n, we have minus 2. X, instead of x, we have h by r. So it's 1 minus 2h by r. So I can use this simplified expansion here. I call this as 1 plus h by r to the power minus 2 is 1 minus 2h as equation number 5. Let's substitute 5 in 4. If I substitute 5 and 4, so the end result is g prime is g 1 minus 2h by r. Instead of this whole expression, 1 plus h by r to the power minus 2, I'm using this term, 1 minus 2h by r. But while using this expression, remember, this result is valid only if h is very, very less than r. If height is very, very less than the radius of Earth. Say the radius of Earth is 6,400 kilometers, r is 6,400 kilometers. So if your h is in meter, like 200 meter, 300 meter, then you can use this approximation. If it is 1 kilometer, then it's better if you use this one. At 1 kilometer, you will have significant error. If it is 200, 300 meter, then you can use this expression. The next is variation of acceleration due to gravity. In the next topic, we will see how this acceleration due to gravity varies with depth. So this is a sphere. This is Earth basically. This is the center of the Earth. The radius of the Earth is capital R. This is the radius of Earth, which is capital R. This is Earth. Mass of Earth is capital M. So I place the body of mass M in some depth D. I place the body in depth D below the surface of Earth. So from the center of Earth, this separation is R minus D. And I call this R minus D as small r. So you have to calculate the value of acceleration due to gravity here in depth D. So consider a point in depth D below the surface of Earth. Below surface of Earth. Now, instead of using the concept of force, I will directly use the expression of acceleration due to gravity. This is the expression of acceleration due to gravity, gm by r square. I will modify this expression only. So now, see with one important thing. If you place mass m in depth d, then total mass of Earth will not exert force over this small m. In fact, this small m will divide Earth into two parts. This will divide Earth into two parts, into two regions basically. There is one region which is inside this small m, this region, this is interior region, and this is the outside the small m, this is exterior region. So if you place a mass m in sub depth d, you dig a tunnel and you put mass m inside the tunnel. So the force over this mass m is exerted by this portion which is this interior portion only. This exterior portion will not exert force on this small m. So the small m basically divide Earth into two parts. One is internal, another is interior, another is exterior. Only this interior portion will exert force on small m. So interior portion of mass m prime will exert force on small m. No, Abdullah. If this, first of all, gravity never push, gravity always pulls. Huh? So this exterior portion will try to attract this mass in upwards direction. But there is this external portion also. This will try to attract this mass in the downwards direction. So the forces due to all these exterior portions would get cancelled out. Only the force due to interior portion remains. So interior portion of mass m prime will exert force on small m. M is mass of Earth. R is radius. Okay, so acceleration due to gravity value of acceleration. Is it clear up to this point? That I took a point in some depth d below the surface of Earth. Due to this mass m, which is placed in the depth d, this mass m will divide Earth into two regions. There is one interior region and one exterior region. Only interior region will exert force on small m, not this exterior region. Now I need acceleration due to gravity here in depth d. So in depth d, the value of acceleration due to gravity is g prime, which is basically gm over gm prime. Say the total Earth is not exerting force here. So even in expression of acceleration due to gravity, we will not consider the mass of total Earth. We will consider the mass of only the interior portion, gm prime, divided by r square. Next, you can write your small r as, see, small r is what? Small r is r minus d. So it's gm prime over r minus d square. That's my first equation. Only one step is left, and that is to calculate m prime. To calculate m prime, I will use unitary method. Unitary method is like, it's like, say you have 10 pen and the cost of 10 pen is 20 rupees. I ask you to calculate the cost of 6 pen. So how would you calculate the cost of 6 pen? You will first calculate the cost of 1 pen, which is 20 by 10, that's 2 rupees. And then you will multiply this 2 with 6. So it comes out to be 12, right? This method is basically unitary method. So in the same way, we will calculate this mass m prime. The mass of the complete Earth is capital M. The radius of the whole Earth is capital R. So the volume of Earth is Earth is a sphere, so its volume is 4 by 3 pi r cube. So I can write this as mass of 4 by 3 pi r cube volume. The mass of 4 by 3 pi r cube volume is m. You have to calculate this, the mass of this volume, this much. The volume is r, the radius is r minus d. The radius of this portion is r minus d now. First of all, I will calculate mass of unit volume, means 1 meter cube volume. That comes out to be m by 4 by 3 pi r cube. This step is equivalent to the step where we calculate the cost of 1 pen. The next you need the mass of volume, which is 4 by 3 pi, it's r minus d cube volume. That you can write m by 4 by 3 pi r cube into 4 by 3 pi r minus d cube. 4 by 3 pi will cancel this 4 by 3 pi. And this is what we are calling m prime. The mass of this 4 by 3 pi r minus d cube volume is m prime. So m prime is m r minus d cube by r cube. That's equation number 2. I'm explaining it again. The mass of the complete Earth is capital M. Volume of the complete Earth is 4 by 3 pi r cube. So I can write this as mass of 4 by 3 pi r cube volume is capital M. Then I need mass of unit volume, which comes out to be m by 4 by 3 pi r cube. Then I need mass of this much of volume. So for this, I just multiply the mass of unit volume with the given volume. So that, and this mass of this 4 by 3 pi r minus d cube is m prime basically. M prime is interior portion of radius r minus. Now, if I substitute these values here, your g prime comes out to be, it's g, instead of m prime, you can substitute these values. It's m r minus d cube over r cube multiplied by r minus d square. So this square will cancel this cube, and g prime comes out to be its gm r minus d over r cube. Okay, the next step is you have to find r small g here. See this gm by r cube. You can write this r cube as, this is gm, it's r minus d over r cube. You have to write your r cube as it's r square into r. This is your r cube. The next step, you can write your gm by r square as small g. You can write this gm by r square as small g. This is the value of acceleration due to gravity on the surface of Earth. This is gm by r square, which is g. So if I substitute it here, this g prime comes out to be g r minus d over r. The next step, you can simplify this thing. You can write this in two forms. G prime is g. You can write this as r by r minus d by r. See, r by r is 1. So g prime is g 1 minus d by r. Is g 1 minus d by r. Or you can just take LCM or write this as r minus d. If you look at the figure, this r minus d is basically small r. So this is gr by capital R. So these are the expressions for the variation of acceleration due to gravity with depth. So if you look at this g prime is directly proportional to r, where r is the separation from the center. If you look at this negative sign simply tells you that the value of acceleration due to gravity decreases with depth. As you keep on increasing the depth of the body, its acceleration due to gravity decreases. Value of acceleration due to gravity decrease with depth. Decrease with depth. Okay. Rania, can you guess the value of d at the center of Earth? This is Earth. And this is the depth, right? This is the center of Earth. If your body is here, then this is the depth. I'm saying your body is at the center of Earth. Then what's the value of d now? This is the radius of Earth. At the center of Earth. Rania. This is d, depth from the surface of Earth. If I place this mass m here, then depth is d. Now I'm saying just place this mass m at the center of the Earth. How much is depth now? Rania. How much is depth at the center of Earth? No answer means you don't know. Fatimatul Naja, will you try?
D is equal to the radius of the Earth.
Oh, very good. Taking this mass to the center, then if you take this mass at the center, then this d will eventually be equal to the radius of Earth. So instead of d, if I substitute r, let's name this equation. Let's call this as equation number 1. Now we already have 1 into it. What's the name of this equation? 3. Let's name this as 3, name this as 4. Put d equal to r in 3. If I put d equal to r in 3, then your g prime would be g 1 minus r by r. Yes, Fatma. See, if I place this mass m inside the surface of Earth here, then from the surface of Earth to this mass, this separation is the depth. This is the depth. If I place the mass m at the center of Earth, if I place this m exactly at the center of the Earth, then the depth will be equal to the radius of Earth, right? Then this d will comes out to be equal to radius of Earth. So instead of d, if I place it, then this is the depth. If I place mass m here, depth is, we always measure depth from the surface of Earth. It comes out to be equal to radius of Earth. So if I substitute d here, it's g prime comes out to be, see g, 1 minus 1. So your g prime comes out to be d. So at the center of the Earth, acceleration due to gravity is 0. Okay, if acceleration due to gravity is 0, then Noor, what's the mass of body? If the value of acceleration due to gravity is 0 here, then what's the mass of the body? Weight of the body, sorry.
The weight of the body is 0.
Right. Because weight is mg. Okay, just note it down. So this is how your acceleration due to gravity varies with depth. This is how its value varies with depth. So always remember this statement, like at center of Earth, weight of body is 0. But not mass. Mass is non-zero. Mass is as it is. If the mass of the body is 2 kg, then this is 2 kg on the surface of Earth as well as inside. Because mass does not depend upon acceleration due to gravity. It is the weight which depends upon acceleration due to gravity. So at the center of Earth, weight of the body is 0, not mass. And this is known as condition of weightlessness. This is the condition of weightlessness. So this is it. Next you have few questions like if the value of acceleration due to gravity at a height h is inversely proportional to r square. In the first equation, I wrote this as this is gm by, with height it was gm by r square. So with height, your acceleration due to gravity is 1 by r square. This is at height. At depth or in depth. In depth, I just have proof that this g is directly proportional to r. So this is outside the surface of Earth. This is inside the surface of Earth. These two expressions will help you to plot g versus r graph. So it's an important question. It will ask you to plot g versus r graph. It will ask you to plot its g versus r graph. This is r equal to 0. R equal to 0 means the center of Earth. By the way, what is the value of g at the center of Earth? Rania? Rania is 1. What's the value of acceleration due to gravity at the center of Earth? We did it just now. Yes, it's 0. Very good. Then r equal to capital R, where capital R is the radius of Earth. This means this point lies on the surface. Here r is less than capital R. Sania, where this point will lie, inside or outside? This is the radius of Earth. If I am taking a point at a separation less than the radius of Earth, this is center, I am taking a point here.
It will go inside.
Inside. But if your r is greater than capital R, which is if the separation is greater than the radius of the Earth,
It will be outside.
this point will lie outside. Okay. So the relation would be inside it will be a straight line graph, linear relation. Outside, see this, the reason of straight line is this expression. If G is directly proportional to R, that means your graph will be a straight line. Outside is 1 by R square. 1 by R square means the shape of graph is hyperbolic. Hyperbolic shape is like this. Means if you go outside, then value of G keep on decreasing. Center at 0, it increase up to the surface. Means if this is Earth, at the center of Earth, the value of G is 0. Then it keep on increasing. It's increasing, increasing, increasing. At the surface, its value becomes 9.8. But once you go outside, then it again start decreasing. 9.6, 9.5, it keeps on decreasing. So this graph tells that center at 0, it keep on increasing up to the surface of Earth. At the surface of Earth, the value of G is maximum. And this value is 9.8 meter per second square. Then as you move outside the surface of Earth, it keep on decreasing, it keep on decreasing, decreasing, and finally it will become 0. Okay, let's erase it. Let's solve one numerical based on this topic, acceleration due to gravity. The numerical says, calculate value of acceleration due to gravity and percentage change with respect to Earth at first, height of 16 kilometer, second part, depth of 16 kilometer. Okay, if I take height equal to 16 kilometer, can I consider this as very, very less than the radius of Earth? Yes or no, everyone? Can I consider this height as this is very, very less than the radius of Earth? Yes or no? Yes, no. So I can consider this height is not very, very less than the radius of Earth. So to calculate height, I will rather use this expression. It's G prime is G 1 plus h by r whole square. Just keep on substituting the values. Is it clear why I'm using this expression, not this one? This expression is valid only if height is very, very less than the radius of Earth. But height is 16 kilometers. It's not very less. The radius of Earth is 6,400 kilometers. So it's somewhat comparable to the radius of Earth. So I cannot use this expression. 1 minus 2h by r, I'm using this one. So this is your G prime. G prime is G. 1 plus h, which is 16, by r, which is 6,400 square. So yours G prime is G. It's 1 plus 16, 464. It's 1 by 400 square. So your G prime is, it's G over 401 by 400 square. So your G prime is, it's 400 square by 401 square into G. This is the value of G prime. I'm not calculating this value. In the next step, you can do one thing. He's also asking to calculate percentage change. Percentage change we calculate in this way. It's final value minus initial value by initial value multiplied by 100. So your G prime is, it's 400 square G. See, G is 9.8. I'm not putting the values, it will waste 2 to 5 minutes. 400 square by 401 square minus G by G multiplied by 100. So you can cancel this value of G. Take G common, so that's 400 square by 401 square minus 1 by G multiplied by 100. So cancel this G. So you are left with only 400 square by 401 square minus 1 into 1. This is the percentage change in the value. See, the calculations in the depth is very straightforward. See, it's in depth if you want to calculate for the part 2. The formula is simple. It's G prime is G1 minus D by R. Just put the value of D as 16 and R you know it's 6400 kilometer. Okay, fine. So if I substitute all these values here, in depth your G prime is G1 minus D by R. Yes, 9.7 seems fine. So it's G1 minus, your D is 16, your R is 6400. So 16400. So your G prime is G. It's 400 minus 1, right? 400 minus 1 is 399 by 400. So 399 by 400, I'm using my calculator. 399 by 400. 399 divided by 400. That's 0.9975 into 9.8. Yeah, it's 9.77. So this into 399 over 400. So your G prime comes out to be it's 9.77 meter per second square. So this is the value of acceleration due to gravity in depth. The next thing that we can do is we can calculate percentage change. Percentage change is G prime minus G by G multiplied by 100. So G prime is 9.77 minus 9.8 by 9.8 multiplied by 100. So this comes out to be, it's minus 9.8. Okay, divided by 9.8 multiplied by 100. It comes out to be 0.25%. Minus 0.25%. Yes, Fazil, percentage change negative means that quantity is decreasing. This negative percentage change simply means that your acceleration due to gravity is decreasing in depth. Fine. Let's do one more numerical. Huh? So I'm erasing it, right? Let's do one. No, I will not solve this numerical. You will solve this. At what height from surface of Earth so I'm giving hint for this problem. The hint is your G prime is 25% of G. Solve this thing and get the value of H. See, with height, the variation in acceleration due to gravity is this. G prime is G 1 plus H by R whole square. So G prime is 25% of G. So you can write this as Like your G prime is 25 over 100 into G. So instead of this G prime, you can substitute this thing. See, this is 25 G by 100, which is G over 1 plus H by R whole square. So this G will cancel this G. 25 by 100 is 1 by 4. It's 1 by 4 is 1 plus H by R whole square. The next thing that you can do is just take square roots on both the sides. Take square roots on both sides. Square root on both sides. If you take square roots on both sides, then this will be 1 by 2 is 1 by 1 plus H by R. Cross multiply it. So 1 plus H by R is basically 1 by 2. Well, one by 2. Not 1 by 2, sorry. 2. So your H by R comes out to be 2 minus 1. Your H comes out to be R. Means your H comes out to be 6400 kilometer. Means at a height of 6400 kilometer, the value of acceleration due to gravity decreased to 25% of its value on the surface. There is one more variation, that is variation with shape. One last variation, that's variation with shape. See, as you know, Earth is not a perfect sphere. Earth is basically an ellipsoid. It's ellipsoidal. This is how the shape of Earth looks like. This is equator and this is polar. It's very clear from this ellipsoidal diagram that this is equatorial radius and this is the polar radius. That equatorial radius is quite greater than polar radius. So if I calculate the acceleration due to this is equator. This is equator. And this is pole. If I calculate the value of acceleration due to at equator, then this is gm over its re square. If I calculate the same value at poles, then it comes out to be gm over its rp square. Now, since equatorial radius is greater than polar radius, so value of acceleration due to gravity at equator is less than the value at pole. This is value at pole and this is value of equator. With height and depth, the value of acceleration due to gravity also change with the shape. It's have different values on equator as well as pole. So this effect is through this thing. It's through the due to the shape of the